So let me erase the sampling point I chose up here just to demonstrate a second ago. Let me just get rid of that. I'm not going to use that. I'm using a right endpoint of this interval. Okay, so that's not the rectangle that will be constructed. It's kind of close, but it won't be the exact one. All right. So since I've chosen right endpoints, that means that on the first interval, right, again, this is the width of some rectangle. On this first interval here, from 0 to 0.5, I'm going to pick the right-hand side of this interval. All right. So here's my sampling point for the first interval, 0.5. I'm going to map that up to the curve. There it is. Okay, so a little bit higher than what I chose a second ago, right? The other one mapped up here. Right. And this will generate the height of my rectangle. Right. And maps down there. Okay, so there's our first rectangle. Okay, it goes higher than the curve in this case. I'm just going to color in a little bit here, maybe something like that. Okay, there's the rectangle we want to calculate the value of. Okay, that's the first one. So let's just look down here. I'm going to start to write out a formula for it, and I'll go back to the second rectangle. So the first rectangle, right here, like rectangle 1. Rectangle 1, I'm going to say, should be, we know its base is 0.5, right? Calculated over here for delta x. So in terms of formula, it would be delta x, right? Whatever that is, the same for each rectangle, times the function, right? Times f at 0.5. Okay? Because 0.5 is where we chose to take the sample from. On this interval, we chose the full right-hand side, so therefore 0.5 into the function will give us this height, and that's the height of the rectangle. So f of 0.5 times delta x should be the area of the first rectangle. But since we're on the squaring function, we're on x squared, 0.5 is just 0.5 squared, and we know that delta x is 1/2. So there's the calculation, right? Not quite yet finished for the area of the first rectangle. I'll do the same thing for the other 3 rectangles. Okay, I hope it's getting clear what's going on here. 3, rectangle 4. All right. So let's finish the drawing. So on the second interval, we're going to pick 1, the far right-hand side of the second subinterval, and map up to the curve here. So that will create a rectangle whose height is 1 and base is 0.5 in this position. There. Next one will be on 1.5. Right? So there's the height that determines the height of the function, the height of the rectangle, height of the function here. Determine height of rectangle. Map it down. And there is rectangle number 3. Now the last one is happening at 2, right? This subinterval here from 1.5 to 2, its right-hand side is 2, so it maps up to the curve here, and the height of the curve determines height of the rectangle, and over and down. All right, I'm just going to draw these in a little bit more. You can see they are all overestimates, right? Each one of these rectangles is more area than it's approximating. Clearly, actual is less than the sum of these 4. All right, so we anticipate in this case our approximation is an over-approximation. Just from the picture, you might not know that when you're working a problem, but it's pretty clear from the picture that has to be the case here. All right, let's go down and write out the formulas and the calculations for the 4 rectangles. The picture is not that necessary for the calculations even, but it does help to kind of visualize what you're doing when you first start doing these problems. So we know this is going to be f of 1 delta x, right? That was the right endpoint of the second interval. And f of 1.5 was the right endpoint of the third interval. And delta x is the same, right? Again, these are all just base times height, right? Height times base for each one. And then we know f of 2 times delta x, base length was the area of the fourth rectangle. So this should be 1 squared, right, because the function is a squaring function. Just replacing the function symbol with the actual operation of squaring, which is what it is in this case. Right, that'll be function dependent for every problem. 1.5 squared times a half, and now 2 squared times a half. All right, so the first rectangle, again, we're going to add those together, right? The whole point is to add these together, and that will be our approximate for the area under the curve. And we know it's over-approximated, in this case, from the way the picture appeared. Okay, so I'm going to add these together. All right, let's just compute this very quickly. Now, one thing you'll notice is that you can always remove the 1/2 value, the delta x value, from these types of summations, right? So let's take the 1/2 out to the outside. So 1/2, because again, all the rectangles are the same base length, so you can always remove that. Now you're just calculating the heights and adding the heights together. So we would have 1/2 times 0.5 squared is, of course, 0.25. 1 squared is 1. 1.5 should be 2.25, if I'm not mistaken. And then 2 will be 4 under the squaring process. All right, now we just add it together. I'll get 1/2 times what? Well, we've got 5, 6.5, it looks like, 6.5. Okay. 6.5, if we use decimals. And then 1/2 times 6.5 is 3.25. Okay, so there is our approximation. And again, we believe from the picture it's an over-approximation. To what? It's over-approximation to the area under f of x equals x squared over the interval 0, 2. Okay?